Now that we know how fast light is, let's start talking about some of its other properties. So hopefully you've experienced this previously, of seeing white light pass into a piece of glass or a prism or a crystal and then getting a rainbow out on the other side. Okay, so we start with white light on one side, and then as it passes through, then we see the light spread out into all the different colors. Where we spread it out into all of the different colors, this is the spectrum. Well, a long time ago, before the time of Isaac Newton, it was commonly believed that the reason why you get colored light out from a prism is that as the light passed through the prism, the glass added something to the light to give color out on the other side. Well, Isaac Newton realized that he could actually test this idea. So what he did is he took white light, passed it through a prism, and then from the spectrum that was produced, chose a single color of that light, and then sent it through a second prism. Okay, if the glass really was adding something to the light, then the second prism would also add more of it to the light, and we should get another rainbow on the other side. So, for example, with this diagram, we chose yellow light. So on the other side, we should get a rainbow, albeit a little bit yellowy rainbow, but a rainbow nonetheless. Well, when he actually ran the experiment and shined the only yellow light through the prism, he found that there was only yellow light on the other side. There was no change. What this means is that the glass didn't add anything to the light. And if the second prism didn't add anything to the light, then the first prism didn't add anything to the light, which means that the white light must already have all of the different colors. All the glass is doing is spreading it out so that we can see the individual colors. Now, you may already be thinking, well, I already knew that white light has all of the different colors, and that's awesome. I'm glad that this is something that people generally already know. But now you know how we know the experiment. And this is actually something you could do if you have a couple of prisms. But it's an interesting experiment nonetheless. Now, as Newton was doing these experiments in optics, which is the physics of light, he felt that the best way to describe how it is that light was behaving was as a stream of particles, that something like a candle or other light source was giving off particles, and those particles would then go through the room, bounce off of surfaces, and then enter into the eye, carrying the light information so that we could see. Around the same time as Newton was doing these experiments, there were other physicists also working in optics, but it was commonly believed by another group that the best way of describing light was not as a bunch of particles, but instead as waves. That waves were being given off by the light source, which would then bounce and reflect off of surfaces and then enter our eye carrying the information. So we have these two competing ideas. Is light particles or is it waves? Well, in the year 1801, a physicist by the name of Thomas Young actually developed an experiment to figure out which is the case. Is light particles or is it waves? So the key here is that there are a couple of things that waves can do that particles can't. Waves can diffract and waves can interfere, and particles don't. Diffraction is where a wave spreads out as it passes through an opening. So, for example, in this image, you can see we have flat waves, what are often referred to as plane waves, entering these two open slits within this barrier. And as they cross, you can see how the waves are nicely curved on the other side. This is diffraction. This is something that waves do and particles don't. If I were to throw a tennis ball through a doorway, it doesn't spread out into the hallway. It keeps going in a straight line through the door. Okay, so waves diffract and particles don't. Something else waves do is that waves interfere. Interference is the way that waves add and subtract as they move over each other. So there are two types of interference. There is constructive interference. This occurs where a wave crest and a crest come together so that they overlap and become extra tall, or a trough and a trough come together and everything gets extra low. Okay, this is constructive interference. As the waves pass over each other, they become larger. The other type of interference is destructive interference. And so in this case, you have a crest and a trough come together, in which case they actually cancel each other out and the wave gets smaller. So constructive interference is where they add up and get bigger. Destructive interference is where they cross over each other and get smaller. And this is, again, something that waves do that particles don't. Imagine you've got two tennis balls and they come and collide together. When that happens, you don't form a giant tennis ball and the tennis balls don't disappear. Instead, they bounce off each other. They reflect instead of interfere in this way. And so again, this constructive and destructive interference is something waves do and particles don't. So Thomas Young developed an experiment looking to see if light diffracts and interferes like a wave, or does it behave as a particle. So the idea is, or the experiment was, what is now referred to as the double slit experiment. The idea is that you have coherent light where we have these nice flat waves, if it is waves, coming in and hitting two small openings. If light is a wave, it will diffract, creating these bends and these new curved waves passing on the other side. Now, because we have two waves on the other side, they are then going to begin to interfere. Some locations will have crests on top of crests, leading to constructive interference. At other points, we'll have crests on top of troughs, leading to destructive interference. Now, when dealing with light, if we get constructive interference, we add light to light, so we get regions of extra bright light. With destructive interference, we have light against light, which means it's going to subtract. So these regions are going to become dark. So if light is a wave, then it will diffract and interfere, and on the other side, where we look for where the light is, we're going to get regions of dark, bright, dark, bright, dark, bright, dark, bright, and so on. Multiple regions where it is light with constructive interference and dark with destructive interference. So that's what would happen if light is behaving as a wave. Now, if light is instead behaving as a particle, remember, particles do not diffract and they do not interfere. What that means is if light is behaving as a particle and it passes through the slit, it can only travel in the direction that it's allowed to, meaning we would get one stream of light from one opening and another stream of light from the other opening, and that is it. The light will not end up anywhere else. So we'll end up with only two bright spots of light if light is behaving as a particle. So if light is a wave, we'll have multiple stripes of light. If it is a particle, we will only have two stripes of light. So when Thomas Young did the experiment, this is the pattern he got, with lots of light stripes and lots of dark stripes. In other words, from this experiment, he was able to show that light diffracts and interferes, and therefore light must behave as a wave. Now, over time, as people were trying to figure out what kind of wave light is, it was determined that light is an electromagnetic wave. What this means is light actually travels because of the properties of electricity and magnetism. We're not going to get too deep into it right now. You can just nod your head and smile at that part. But do remember that light is an electromagnetic wave. Now, one of the key properties for any kind of wave is the wavelength. The wavelength is the distance from one crest to the next crest. Okay, so it's the length of the wave from crest to crest. Now, for light, the wavelength is associated with the color that we see for the light. I'll show you more about that in just a little bit. Now, as people continue to study light, it was shown that there are other types of light than just what we are able to see. There's an entire spectrum, an electromagnetic spectrum of light. Here is the entire electromagnetic spectrum, and we're going to be looking from longest wavelength to shortest wavelength. So, starting at the very longest wavelength, we have radio. Radio is actually a type of light. When I say radio, you probably don't think light. You probably think of the magic box that somehow produces sound when you have it plugged in and turned on. Well, the reason that it is called a radio is because it's receiving radio light from the broadcast tower. So a radio is still a magic box, but it's a magic box that converts light, radio light, into sound. Going to shorter wavelengths, so radio has the longest, and then going to shorter wavelengths, we then have microwave. Then shorter wavelength for microwave, we have infrared. Then shorter than infrared is visible light. Now, because visible light is the type of light we see, we subdivide it into the different colors. Red light has the very longest wavelengths, and then going to shorter, we have orange, yellow, green, blue, and violet, with violet light having the very shortest wavelengths of visible light. After visible light, we then have ultraviolet. Then even shorter than ultraviolet are X-rays, and then even shorter than X-rays, and the shortest of all electromagnetic waves are gamma rays. Gamma rays have the very shortest of all the wavelengths. As we continue to study light, we found that this order also happens with the amount of energy and with the amount of frequency, the frequency of the light. So radio waves have the very least amount of energy and the very lowest frequencies. Gamma rays have the very, very highest energies and the very, very highest frequencies. So at this point, we feel like we've got a good understanding of light. Light is just an electromagnetic wave, and we understand the wavelengths and the energies and so on. The problem is that as we do other experiments, it actually shows that light has to behave as a wave. The first experiment that really demonstrated this was what is known as the photoelectric effect. So photo means light, electric is like electricity. So what happens is we shine light onto a piece of metal, and that metal can then eject electrons. This is actually similar to how a solar panel works. You shine light on, you get electricity out. It's not exactly the same thing, but it is related. Well, as people were experimenting with the photoelectric effect, they found something very interesting. What was important about to determine how many electrons and how fast the electrons were leaving the metal was not the intensity of light, but it was the wavelength or the color of light that was important. If light was actually behaving as a wave, the more intense the light is, the more energy that wave should be giving to the piece of metal, and therefore the more and the faster the electron should be ejecting. But that's not what happened. What they found is that it was all determined by the color of light. So, for example, if they shined red light onto the piece of metal, no light would ever escape. No matter how bright, how intense that red light was, no electrons would ever escape. But even using faint green or faint blue light, they were able to get some electrons to eject. Now, if they increased the intensity, more electrons would eject, but it seemed to be more color dependent or wavelength dependent than intensity dependent. Well, trying to explain this, Einstein proposed that in this case, light was actually behaving as a particle, and that each particle of light had an amount of energy determined by its wavelength or color. So the particles of red light, no matter how many red light particles you have, no one of them had enough energy to give to an electron to cause the electron to jump out. But green light, even one photon of green light would have enough energy to cause the electron to jump out of the metal. So in this way, light must be behaving as a particle. Another example where light must behave as a particle is actually photography. Old-fashioned photographic film and even new electronic photography devices only work if light is behaving as a particle. The CCD, the piece that is actually taking the picture in a digital camera, actually counts the photons. And you can't count a wave. So it's counting individual particles of light. Light has to be a particle. So is light a wave? Yes, it can behave as a wave. Is light a particle? Yes, it can behave as a particle. So what is it? That's still an ongoing question. This mystery of exactly what light is has created an entire new branch of physics known as quantum mechanics. We're going to touch on quantum mechanics here and there throughout the class because we have to explain some of the things that we're dealing with. Don't worry, we're not going to deal with it too much, just a little bit. But it leads to some very weird things, as you can already tell with the what is light question. We actually use all of the different types of light in many modern devices. We have been studying light for several centuries, and now we actually use it, pretty much all of the different types. So, for example, radio. I already mentioned that radio light is what we use for radios. It's also what we use for cell phones. Microwaves. When I say microwave, you probably think heating up food. Well, the way that it heats up that food is through microwave electromagnetic radiation. There is a very specific frequency, or you could think color or wavelength, of microwave light that interacts very, very strongly with water and oil. This will cause the water and oil to start rotating and moving faster and faster, which then heats the rest of the food. Okay, infrared, as you can see, we've got a picture of a remote control. If you've ever looked at a remote, you've noticed there's a little light bulb on the front of the remote, and no matter how much you press the buttons, it never seems to flash. That's because it's in the infrared, and our eyes don't pick up infrared. However, some cell phone cameras actually can. So the next time you're alone, so that nobody can watch you and judge you, go ahead, pull out your remote and your phone, and see if you can see the flash when you hit the button, as your camera is picking up the infrared light. So what do we use visible light for? Yeah, this is the one we see with. This is what we normally think of as light. Okay, continuing on to shorter wavelength and higher energy, we then have ultraviolet. Ultraviolet light, as you can see pictured here, is used for tanning, or at least for some people. For me, it's used for getting burned. Actually, although this image is showing tanning, there are some really good uses for ultraviolet light. For example, it is used in certain types of disinfecting. A lot of microbes are actually very damaged by intense ultraviolet light. Continuing to shorter wavelengths and higher energy, we then have X-rays. And you're probably thinking of X-rays, like what we get from a doctor, where you can actually see the bones. In this case, what's happening is that the light is becoming so energetic that it's actually able to pass through the soft tissues of our bodies, but actually becomes blocked by the hard tissues. So you can actually get an image of the hard tissue in your body. And gamma rays are just now starting to be used for certain types of cancer therapies. We can actually focus the gamma rays and literally kill the tumors while they're still inside the person, so that we don't have to resort to surgery, which can be very risky. Now, gamma ray radiotherapy is relatively new. It is still not widely used, but we're figuring it out, and it's getting better. Now, in astronomy, we want to be able to use all of the different types of light. And the reason for that is because different things interact with the different types of light in different ways. Some objects will give off radio, but not give off visible light. Or they will give off visible, but absorb radio and X-rays. Okay, depending on the spectrum, the part of the spectrum that we're looking at, we can actually get different types of light. So there are radio astronomers and visible light astronomers and X-ray astronomers. All of us trying to look at different parts of the spectrum to learn as much as we can about the universe around us. So here's our first lecture quiz question. Which color of light has the highest energy? A red, B yellow, C green, or D blue? Go ahead and think about it, and we'll discuss in just a bit. All right, do you remember which color of light has the highest energy? The correct answer is D. Blue light has the highest energy. In fact, as we go down A, B, C, and D, we're actually increasing in energy, with red light having the least energy. So something I want to warn you about. In physics and astronomy, for some reason that I haven't figured out yet, we say blue light has the shortest wavelengths. It really doesn't. If you remember, violet has the shortest wavelength and the highest energy, but we talk about blue as if it does. So in class, if I'm talking about this is very blue, Then interpret that as short wavelength, high energy. However, if on an exam I ask what has the shortest wavelength or the highest energy, make sure you actually answer violet.